Welcome to part 3 of a 6-part series where we will explore using the Intel Quartus Prime Pro software. In part 3 of this series, I will go over the physical layout tools that exist in the Intel Quartus Prime Pro software. First, I will go over the pin planner. The pin planner is the main method for creating I/O-related assignments in the Intel Quartus Prime software. Location assignments can be made by simply dragging and dropping signals onto the desired I/O pins. You can set the I/O standard for a bank of pins with the standards available for your selected device and reserve I/O locations for future assignments. Any I/O-related assignment that can be created in the assignment editor can be created in the pin planner. The pin planner is open from the assignments menu, the toolbar, or the tasks window. The pin planner is made up of several default sections: the package view, the all pins list, the groups list, the tasks window, and the report window. To access Pin Planner from the software, you can click on the Pin Planner button in the main toolbar, use the Assignments pull-down menu and select Pin Planner, or you can navigate in the Tasks panel and launch Pin Planner from there. Here's what the Pin Planner looks like when you open it. The toolbar has a minimal set of default buttons, but you can add additional buttons using the Customize option found in the Pin Planner Tools menu. The Package view is the main way to create I/O assignments because you can visually see where I/O signals are located. You can create or edit any assignments in the package view. The package view also displays pins that are not user I/O, such as power and device configuration pins, to ensure that signal assignments are not made on those pins. Different views available for the package view use color and highlighting to provide different types of information about package pins. The All Pins list displays a complete list of all the I/O signals in your design. Any buses in the design are expanded out into their individual signals. With the package view and the All Pins list, I/O assignments can be created for each individual signal in the design. The groups list is similar to the All Pins list, except that only buses and custom signal groups are listed. With the groups list, you can quickly create I/O assignments for all the signals on a bus. You can also create a custom group of signals and create assignments for that group, even if the custom group signals are completely unrelated to each other. The Tasks pane is similar to the Tasks pane in the Chip Planner and the main Intel Quartus Prime software window. You can quickly execute tasks in the Pin Planner, such as early I/O planning or generate Pin Planner reports. Much like the Chip Planner, these reports are stored in the Report pane where they can be enabled or disabled as desired. In the same panel as the Groups list, you will find a tab for the reports that are generated. The generated reports are color-coded so that you can easily associate the pins in the package view with the reports. And finally, there is the Pin Login panel. The panel lists the pin types that exist in the FPGA. There are a number of ways to create I/O location assignments in the Pin Planner. The simplest is through drag and drop. Select a signal from the Groups or All Pins lists, then drag and drop it onto a pin in the package view. As you hover the cursor with the signal over pins in the package view, tooltips appear to provide information about some of the functions of the pin to help you decide whether to place the signal at that location. If you drag a group from the Groups list or a selection of multiple signals from the All Pins list, you can decide how to place the signals in the package view using buttons in the toolbar and options in the Edit menu. The default option is to assign the multiple signals one by one. After you assign the first signal, the next selected signal becomes attached to the cursor, allowing you to click in any location to create its assignment. This continues until all selected signals are assigned. Press the Escape key at any time to cancel. You can also choose to assign all the selected signals in a particular direction. When you select one of these options from the Edit menu, all the selected signals get attached to the cursor in the direction selected. This makes it easy, for example, to place an I/O bus on the outside row or column of pins. If a location assignment cannot be made to a pin in the selected row or column, such as a power pin, the signals that can be assigned will be, while the remaining signals will skip over the unassignable pins to be placed at the next assignable locations. If the number of signals selected exceeds the end of the available locations in a row or column, the remaining signals remain attached to the cursor for assignment elsewhere. As you can see, drag and drop makes it very easy to create location assignments. Not only can you drag and drop signals to specific pins, but you can assign signals to the boxes that surround the package view for assignment by the fitter. The boxes around the package view are different depending on the view selected. We'll look at the different types of views in a little bit, but the views represent different groupings of pins, such as by I/O bank as shown here. By dragging and dropping signals to these boxes, the fitter will assign the selected signals to pins that belong in the grouping, This is a good way of creating I/O assignments for a large number of signals at one time if you are flexible with their final location. Instead of assigning by going from signal to pin, you can assign by going from pin to signal using the Pin Properties pane. Right-click or double-click any pin in the package view, or use the View menu to access it. You can select the signal to assign from the node name list and set the pin's I/O standard. The Pin Properties dialog also includes a small table that provides information about the pin and its dedicated functions. In the process of creating I/O assignments, you may have hundreds of signals in your design. To focus on only a certain type of signal, select a filter in the All Pins list. By default, the All Pins list displays all signals in the design, but you can choose to focus only on unassigned signals, or only inputs or only outputs, for example. Yet another way of creating I/O location assignments in the Pin Planner is through the location column cells in the All Pins list. Double-clicking a cell displays a list of all pins and I/O banks in the device, color-coded by I/O bank. Select a particular pin or select an I/O bank to have the fitter select a particular location in that bank. As mentioned earlier, any unassigned signals are automatically placed by the fitter when it runs. Normally, these assignments are not visible, so you can focus on creating your own assignments. To view the fitter placements, click the Show Fitter Placements toolbar button, or select it from the View menu. An icon in the lower left-hand corner of the package view indicates that fitter placements are being displayed. Fitter-placed I/O appear as green pins in the package view. If you like how the fitter has placed I/O signals in the device, you can choose to use those assignments instead of manually creating assignments using the techniques discussed so far. However, if a change is made to a setting and the fitter is run again, it's possible for the fitter to place a signal in a different location. To prevent this from happening, you can use a feature called back annotation. Back annotation takes fitter assignments and locks them into place by turning them into user assignments and writing the assignments to the KES file. User assignments always have priority over fitter assignments, so if the fitter chose different signal locations in a future compilation, those assignments would be ignored. Select Back Annotate Assignments from the Assignments menu to lock the fitter's assignments into place. You can see back annotated I/O assignments in the Pin Planner package view. You may have noticed in the pin legend that user I/O assignments are colored reddish-brown and fitter I/O assignments are colored green. When fitter assignments are back annotated, pins take on a green and brown hatch pattern to indicate that the locations are now both fitter assigned and user assigned. The Pin Planner includes a few other features to help in making I/O assignments. The package view features a number of different views to help organize device pins. We've already discussed I/O bank view, which is the default view, but you can choose to view the package by device edges, essentially dividing the package into 4 quadrants, by voltage reference groups, or turn on an option that indicates dedicated differential pin, pairing for differential I/O standards. The positive and negative pins of the pair are joined together by small red lines, as shown here. For DDR type interfaces, you can view the package by DQ/DQS banks, as we'll see next. Other views listed here may be available depending on the hardware resources available in the selected device. You may have noticed that the pins in the package view take on different colors, shapes, and labels. These visual indicators help to understand the available functions of pins without always having to refer back to the device handbook. To understand and keep track of these indicators, open the pin legend from the View menu or toolbar. The legend explains all the indicators you'll see in the package view. For example, triangles pointing up and down represent power and ground pins, respectively, while the PN and labels indicate the positive and negative pins of a differential pin pair. As an example of what you'll see with the available views in the Pin Planner, here's what the DQ/DQS view looks like. DDR memory byte lanes contain a number of data pins clocked by a strobe pin or a differential pair of strobes. Turning on the DQ/DQS view highlights the pins in the target device specifically designed and optimized for this function. You can view by 4, by 8, by 16, or by 32 depending on the capabilities of the target device. For more information, see your selected device's handbook to learn more about interfacing with the DQ/DQS pins. Other views highlight the pins required for using hard IP features of the selected device. You can view the pins required for connecting to the hard memory controllers or the hard PCIe blocks. This makes it much easier to make location assignments for the signals required when using these features. Much like the chip planner, the Pin Planner has tasks and report windows. As mentioned earlier, the Tasks window gives you quick access to common tasks performed in the tool along with the ability to create custom task views of the device I/O pins. These custom views are available in the Highlight Pins folder in the Tasks window. A report generated from these tasks is a colored overlay displayed on the package view. Unlike the background views discussed earlier, multiple reports can be created and enabled simultaneously, allowing for completely custom views of the package I/O. All generated reports can be easily enabled or disabled from the report window. During a normal compilation, the fitter will place all unassigned pins in locations that will ensure that all design constraints are honored. This includes signals that were assigned to particular I/O banks or the other boxes that are available through different views in the package view. If you have particular pins that you don't want the fitter to ever assign signals to, perhaps because you have not yet added a particular I/O signal to your design, you can set those pins up as reserved pins. You can give reserved pins a custom name using the new node cell at the bottom of the All Pins list, or have the tool automatically name them User Reserve. In the Reserved column in the All Pins list, double-click and select whether the reserved pin should be bidirectional, a tri-stated input, or a driving output depending on how the reserved pin should operate if the target device is programmed with the reserved pin assignment still intact. Reserved pins will appear blue in the package view. As a side note, it's a good idea to go to the device settings and select the initial state for other unused pins using the same options available for reserved pins. Do this to make sure that the state of these pins is in line with their potential connections to the printed circuit board. We'll look at how to do this in a moment. Next, let's talk about Chip Planner. The next compilation results tool is the Chip Planner. The Chip Planner presents a graphical view of the target device with the resources selected by the fitter to implement the design highlighted. You can change the display to view different types of information, including the routing channels between different resources and clock domains that use global routing resources. The Chip Planner is very useful for seeing how the fitter placed design logic and how it connected that logic together, but you can use the Chip Planner to change logic locations or force the fitter to place logic in certain locations. The Chip Planner will become an essential tool for debugging any issues related to the placement of design elements in the device. The next tool is the Chip Planner. You access the Chip Planner through the toolbar, the Tools pull-down menu, or through the Tasks window. This is what Chip Planner first looks like when you open it up. There is the toolbar on the left for you to perform some of the more common Chip Planner functions. The Tasks window is mainly used to generate reports about your loaded design. The reports can then be accessed in the Reports window above the Tasks window. When you select an object in the main Chip View window, details about the object's properties are displayed in the Device Properties window. A log of cross-probed objects is maintained in the Locate History window. As with the other tools in the Intel Quartus software, Chip Planner can be scripted and also has a ready-to-use Tickle console. Like the netlist viewers, the Chip Planner also includes a bird's eye view to help in navigating around the chip without zooming in and out. With the bird's eye view visible, dragging the small square moves the view of the main Chip Planner window without having to manually scroll the view or zoom out. The square directly correlates to the view in the main Chip Planner window. Chip Planner can help you navigate your design with a split window option so that you can work on two sections of your design. To help in design analysis, the Chip Planner includes tasks and report windows. These windows allow you to quickly generate useful views of the chip without having to create custom tasks or adjust any layers settings. Reports are generated by simply double-clicking a task in the Tasks window. Some tasks may open a dialog box where the report can be customized. Once a report is generated, it appears in the Report window and the results are overlaid on the existing chip view. Different types of generated reports will overlay different types of information in the chip view. A generated report may include many different types of information, from the simple block coloring, shown here, to detailed area highlighting, connection lines, heat maps, or labels. Some reports may even include unique contextual menus, allowing for further analysis depending on the object in the report that gets right-clicked. Tasks are updated, and new tasks are added with each new version of the Intel Quartus Prime software. Once a report is generated, you can control its visibility in either the Layers settings or in the Report window. Disable the Report Overlay option in the Layers settings to completely disable viewing of all reports. Depending on the report, use the options in the Report window to enable or disable the entire report or just individual aspects of the report. You can also use the Toggle Background Colors task to de-emphasize other colors in the chip view. When this task is run, the colors of all other objects turn gray, allowing you to focus on the report overlay. The Chip Planner models types of resource objects as unique background display layers and uses tasks, predefined sets of layer settings, to control the display of resources. The chip planner provides a set of default tasks, but you can create custom tasks to customize the display for your particular needs. The basic, detailed, and floor plan editing tasks provided with the chip planner are useful for most analysis and assignment-related activities. You can also make a number of floor planning assignments directly in the chip planner by opening the Location Assignments or Logic Lock plus Regions windows. Location assignments are used to manually place design elements into specific physical locations, essentially overriding the fitter. Creating Logic Lock plus Region assignments divides the device floor plan into physical partitions. Design elements are then assigned to each region, and the fitter must place all the design elements within the assigned region. This is useful for team-based designs and for forcing proximity on parts of the design that may have difficulty in meeting timing requirements. The chip planner uses a hierarchical zoom that shows various abstraction levels of the targeted Intel FPGA device. As you zoom in, the level of abstraction decreases, revealing more detail about your design. If you are zoomed all the way out, you can see the total logic resource usage in the device, indicated once again by the darker colored block resources. Zoom in closer, and you can see more detail and which blocks are used. Zooming in even closer displays low-level routing detail if the option to view it is enabled in the Layers settings. Within the chip planner, when you highlight a resource used by the design, detail information about that block, including a diagram with the used parts of that resource highlighted, is displayed in the Node Properties window. Here you can see a logic cell has been highlighted. In the Node Properties, you can examine the inputs, outputs, and lookup table, or LUT, masks associated with that logic cell. If you double-click a used resource, a tool called the Resource Property Editor appears. Logic lock regions are floor plan location constraints that help you place logic on the target device. When you assign entity instances or nodes to a logic lock region, you direct the fitter to place those entity instances or nodes within the region during fitting. Your floor plan can contain several logic lock regions. A logic lock region is defined by its height, width, and location. The coordinate system is based off of logic array blocks or labs. A lab consists of 10 adaptive logic modules, or ALMs. Each ALM will have 4 registers and 4 input lookup tables. To create logic lock regions in the chip planner, first create a logic lock region using one of the methods from the last slide. Then a logic lock region will appear in the chip view of the chip planner. Using the arrow tool, you can change the size of your region and drag it to the desired location on the FPGA. You can also use the Logic Lock Regions window inside of the chip planner to change the properties of your logic lock region. Click on a cell within this table to change the size and location of the logic lock region. Your change will be reflected in the rectangle within the chip view. You can also change the reserved, core only, and routing region properties from this window. When you create a floor plan for your design, you may want to create non-rectangular logic lock regions to exclude certain resources from the logic lock region, or to place certain parts of your design around specific device resources to improve performance. To create a non-rectangular region, first create an unassigned region by right-clicking on a new row in the Logic Lock Regions window and selecting Assign Logic Lock Region. Next, size the region to your desired size. The next step is to move the unassigned region to its desired location in relation to the region it will be merged with. Overlap regions for non-rectangular contiguous logic lock regions. Keep them apart for a non-contiguous region. Select both regions by using Ctrl+Click or by drawing a box around both of them. Right-click on this selection and choose Logic Regions, Merge Logic Lock Region. Nested or overlapping logic lock regions match up with the design hierarchy. Because of this, overlapping regions restrict the placement of lower-level design instances. These child instances are constrained to the region of their parent. If a region constraint is added to the child, this constrains the placement of further lower-level instances. In the example shown here, a BC is constrained to the region in the upper right. Without any additional constraints, all logic for a B key and any lower-level logic, its children, would be constrained to just this region. A second region constraint is added for a B seed overlapping the first region. Now a B seed logic can be placed in the area of the second region outside of the original B region. However, since the two regions overlap, any child instances of a B seed are constrained by a B C's parent. Thus, logic, such as a B seed E, would be constrained to the intersecting region. Be aware of this when recreating your floor plan with logic lock regions. The reserved parameter, set to off by default, tells the fitter that other elements can be placed in the logic lock region. When it is set to 1, then only elements belonging to the module will be placed in the logic lock region. The routing region is set to unconstrained by default. This means that routes that belong to the constrained module can use the entire FPGA, if needed, to complete the routes. Let's take a look at the other routing region options. The default of unconstrained and whole chip are identical in purpose. Whole chip is an actual parameter that gets passed in, whereas unconstrained is when no parameter gets passed. You can also constrain the routing to a specific region if you need to. There are 2 types of routing regions constraints: fixed with expansion and custom. The routing region of expansion length adds the number of labs specified around each side of the logic lock region. The expansion length has to be at least as large as the logic lock region itself. The fixed with expansion length routing region allows you to create a rectangle that is at least as large as the logic lock routing region, but the additional labs on each side can vary, as opposed to the fixed with expansion where the addition was the same for each side. Finally, let's take a look at Interface Planner. The tool to use to meet these needs of placing complex I/O interfaces following all required placement rules is the Interface Planner. Interface Planner allows you to create legal assignments graphically using the power of the Quartus Prime Fitter. Interface Planner works with the fitter to verify and validate design element assignments in real time, giving you the ability to create and complete your I/O floor plan in minutes instead of days. You can provide your floor plan to your board designer much earlier in the design flow, allowing you to have boards built with confidence knowing that the layout is correct for the device. Interface Planner is found only in the Quartus Prime Pro Edition software. As such, Interface Planner can be used with ARIA 10 and all newer device families. Interface Planner is very easy to use. It has a well-defined usage flow that you can always view in the flow window of the tool. The flow window can be hidden with the indicated button and made temporarily visible again by clicking the gray flow bar. Grayed out items in the flow window indicate tasks that have already been performed or that require other tasks to be performed first. Instructional dialog boxes also appear to walk you through the steps. The complete flow is listed here, and we'll look at each step in detail. First, set up the project to prepare for working with Interface Planner and synthesize the design. As mentioned earlier, the design you want to use with Interface Planner must first be synthesized. Once this is complete, the project is opened in the tool and initialized. Next, any conflicts between existing Quartus Prime assignments that were imported during initialization must be resolved, and the Interface Planner plan must be updated with the resolutions. You'll then actually create your Interface Planner plan by placing design elements, including entire I/O interfaces, into resources on the device. The finished plan must then be validated against the imported assignments. Finally, the new Interface Planner created assignments are written out as a tickle script, which is then sourced into the Quartus Prime project. To get started, you must prepare your project for use with Interface Planner. The preparation required is minimal. Interface Planner can be used at any stage of the design process, and you can return to the tool to update the plan and create new assignments at any time. However, there are a number of things listed here you can complete in your design to prepare it for design planning with the tool. Before using Interface Planner, you should have all I/O interfaces defined, either in the top-level design entity HDL code or through the creation and instantiation of I/O-related IP cores, such as external memory interfaces or PCIe standalone general-purpose I/O, should also be defined along with any associated assignments, such as I/O standards, voltages, drive strengths, and slew rates. Clock domains should be defined to allow for clock resource assignment in Interface Planner, but this is not required. Finally, depending on the completeness of the interfaces in your design, you may want to create virtual pin assignments or attach I/O to test logic or loop interfaces. This prevents I/O from being optimized away during synthesis if internal design connections are not yet complete. When you are ready, perform a full synthesis of the design. As mentioned earlier, this is required for working with Interface Planner. Once the design is synthesized, open Interface Planner from the Quartus Prime Pro Edition Tools menu, the toolbar, or command line. Interface Planner uses the Quartus Prime compiler, specifically the fitter, so if you open the tool from the GUI, the Quartus Prime software must be closed when Interface Planner is opened. The tool opens with the flow window and the Home tab displayed. If Interface Planner was opened from an already open Quartus project, that project and its current active revision are selected on the Home tab. You can create plans for other projects or revisions by selecting them from the Home tab or the File menu. Once the design is initialized, a basic summary report appears on the Reports tab. We'll look at Interface Planner reporting in more detail later, but this report provides a list of all IP cores that require placement in the device along with the status of placed versus unplaced design elements. The assignments that were imported during initialization are checked for conflicts and legality and listed on the Assignments tab. If there are any issues reported, you can choose whether each assignment should be enabled or disabled, or simply enable or disable all the listed assignments. This sets up how the floor plan will be checked against the existing project assignments during the planning stage. Once you've set the status of each assignment, click Update Plan in the Flow window to begin creating the floor plan. Now you are ready to create the interface plan. The interface planner resembles the other floor planning type tools that you have seen. There is a design panel that has all of the design elements that can be placed. When you select one of those design elements, the information about that design element will be listed in the panel beneath the design panel. When you click on the two greater than symbols in the design panel next to one of the elements, all of the legal locations come into view in the main chip view window with the locations outlined in black. Also, textual list of locations come up in the legal locations panel on the right. You can either drag and drop the design element into a legal location in the main chip view, or you can double-click on a location assignment in the legal locations panel to place the interface. Once the interface has been placed, the legal locations will update so that you will know other locations for the same type of interface. Down in the lower right, there are Undo and Redo buttons to help with placement in the event you need to change locations of the interface. You can change the color coding of the interfaces by right-clicking on the design element and selecting the color that you want. There are the Save Load and Reset Plan buttons to help with your project. Auto Place All will allow the tool to place all of the interfaces in your design. Auto Place Fix tells Interface Planner to place all of the interfaces that have only one location available for placements. And Unplace All, as the name suggests, will unplace any place interfaces. You can also right-click on the interface and have Interface Planner place the element. The main view has been changed to a package view, giving you a visual description of what the pins of the placed interface look like. If you look closely, you will notice that some of the pins are bolded in black. These pins represent the starting placement pins for available interface locations. After you are done with your interface plan, click on Validate Plan to run the design rules. Check to make sure your interfaces are in valid locations. You will notice that two interfaces have been placed, and you can see the color coding of the two interfaces in the Package View window. Now what you will want to do is to export your constraints. The resulting file is tickle-based and can be used in your Intel Quartus Prime software project. You can source this newly created tickle file in the QSFs so that the assignments will be made in your project. Thank you for taking this course. In this course, we went over the physical layout tools that exist in the Intel Quartus Prime Pro software. Intel provides multiple avenues in which to learn about Intel FPGA products. There is the Intel FPGA YouTube channel, which contains 5-minute quick videos along with longer, more in-depth training videos. There is the Intel FPGA training website, where you can access e-learning courses made up of narrated slides presented in an interactive player, some courses with labs and demos. Lastly, you can also enroll in a live, instructor-led course presented either in person, at an office local to you, or virtually over the web. All instructor-led courses have hands-on labs exercises to practice the concepts you learn. If you need more assistance, Intel FPGA provides many self-help resources for you to access. For example, there are web pages called landing pages dedicated to specific FPGA technology like and high-speed interfaces. You can also view and post questions to the community forum, which is monitored by skilled Intel FPGA applications engineers. The Intel FPGA training team is always looking to improve our material and welcome any feedback you may have. Please email fpgatraining@intel.com with any of your thoughts or comments. Thank you for listening to Part 3 of the series, Intel Quartus Software Physical Layout. Check out our other 5 parts in this learning series.